All right, welcome to Chapter 9, Lesson 2, where we're going to be comparing two populations or groups by using two means instead of two proportions. So after this section, you're going to be able to describe the center, shape, and spread of a sampling distribution of the difference between two sample means. You'll be able to determine whether the conditions are met for inference about mu1 minus mu2, and that's just making sure you have your normal condition, your simple random sample, and your independence condition. You're going to construct and interpret a confidence interval to compare two means, and finally, you'll perform a test of significance to compare two means, and you'll also understand the difference between a two-sample t procedure versus a paired t procedure, which we learned in our previous lessons was actually a one-sample t-test. Okay, let's take a look at the first one. The first example is an example of a matched pairs t-test, which is a one-sample t-test for means. The Glista Recycling Group claims that they can reduce the amount of non-recyclable waste produced by the McLean Pyramid of Schools. Below are the non-recyclable waste totals for January, before the Glista group, and February after the recycling has begun. If there is a significant reduction of non-recyclable waste, the Glista group will be awarded the contract. Waste in this example is in tons. If we want to test the claim that the group has reduced the amount of non-recyclable waste at the alpha equals 0.05 level, what kind of test will you use? What you're going to want to think about here, remember, is with the matched pairs, are the two pieces that you're looking at, are they independent or are they from the same population? So if we take a look at this one we're going to use matched pairs. Why? Because it is not two independent samples. It's two samples, but it's a before and an after. It's still only one population. I'm not taking the information from two different populations. I'm taking information from one population in January and then that same population again in February. The two samples are not independent of each other. So just kind of be on the lookout for that as you're looking for a two-sample t-test versus a matched pairs. So in this section, we're going to be looking at testing the difference between two means. So before we do that, we want to determine how are we going to tell the difference between matched pairs and the difference between two means. You're going to start thinking about whether or not the samples are independent or not independent. So when you're looking at your table, are they from two different populations or one population? If the two samples are independent or from two different populations, then it's a difference between two means. The Glista example was a matched pairs because it was from one population, one school in the McLean Pyramid, and I broke it up into two different time periods within that same one population. So what exactly does comparing two means, how does that look different? And why would we do that? We often use comparative studies because they're more convincing than single sample investigations. One sample inference is not as common or as provides as much convincing evidence as a two sample for inference. And in a comparative study, this way we can compare true treatments, so they're two different treatments, so two sort of populations, or two different populations. In either case, please make sure that the samples must be chosen randomly and independently in order to perform statistical inference. So that means not only you have two simple random samples, one from population 1 and one from population 2. Now, because the matched pairs are not chosen independently, we will not use a two-sample inference for matched pairs. So just be careful. Remember, that means that population 1 is different from population 2. That's not true in matched pairs. For a matched pairs design, you're only using a one-sample T procedures on the differences that you're subtracting. So remember, you kind of actually get rid of those two samples that you looked at, and you just look at that one set at the bottom, which was your differences. So what I want you to think of is a matched pair study. The subjects are matched in pairs and the outcomes are compared within each matched pair. Or a before and after, Randomization isn't possible, so matched pairs is used always, and you make sure you're always doing the after minus the before. So this is just a review of what you actually did in the last section. All right, so now let's take a look exactly what is a matched pairs, or what is a two-sample t-test, and how is that different from matched pairs. So what if we want to compare the mean of some quantitative variable for the individuals in population 1 and population 2? The parameters of interest that we're looking at, instead of having one mean, we're going to be looking at a mean of my first population and a mean of my second population. Since I have two individual populations, I'm going to have to take two separate random samples from each population and in the end compare those two sample means. So let's say we want to compare the average effectiveness of two treatments in a completely randomized experiment. We will then use the response in the two groups to make the comparison. So you have experiment 1 and experiment 2. You will compare the separate results of those two experiments to see whether or not they're different. So I just wanted you to take a look at what your symbols are going to look like. So you're either going to have two different treatments or two different populations. Your parameters are going to be mu1 and mu2, and it's very important that you label them 1 and 2 to show that we have two different populations or two different treatments for our means. Your statistic, and remember your mean is always going to be what you're going to write your null and alternative off of. Your statistic is x bar 1 and x bar 2. So that's the sample that we gather. And just keep in mind, we're always gathering that sample after we've come up with the null and alternative hypothesis. And then our sample size, once again, is N1 and N2. So just make sure you're labeling everything with your 1s and 2s to keep the two different populations or treatments separate. Okay. All right. Now, in order to explore the sampling distribution of the difference between two means, let's start with two normally distributed populations having known means and standard deviations. Based on the information in the U.S. National Health and Nutrition Examination Survey, the heights in inches of 10-year-old girls follow a normal distribution with a mean of 56.4 and a standard deviation of 2.7. The heights in inches of 10-year-old boys are approximately normally distributed with a mean of 55.7 and a standard deviation of 3.8. Now, suppose we take independent simple random samples, so that means the girls and boys are separated, then I take the samples of 12 girls and 8 boys of this age and I measure their heights. What can we say about the difference, or x bar of my female minus the x bar of our male, in the average heights of the sample of girls and sample of boys? So we're saying here, is there a difference between the two heights? Now, this is not matched pairs, once again, because we have two different populations. Population 1 is girls and population 2 is boys. And we're not doing a before minus an after. We're checking to see, is there a difference in the two population heights? Okay, so let's take a look and see what this looked like. Our first graph that we have down here is a simple random sample of 12 girls, and we did this 1,000 times, and then we found the mean of all of those 1,000 samples of 12 girls. That mean was 56.4 with a standard deviation of 0.8. The second one, I took a simple random sample of 8 boys, found the mean, plotted it. Took another simple random sample of 8 boys, found the mean, and plotted it. That's what each of those dots mean. And this process was repeated 1,000 times. So for this graph, it means I have 1,000 samples of size 8. Their boys' mean height was 55.73 inches with a standard deviation of 1.35. Now, let's take a look at the sampling distribution of the differences. So what that means is every single solitary point on here, I took, okay, the sample from the female and subtracted the sample mean from the males. So I literally took every point on here and did subtract. subtract, 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 subtract. Okay, what does the difference in the means look like? Now notice we have a 0 down here. So that means if I took the girl's height minus the boy's height and the mean was 0, that would say, hey, there is no difference in height. The boys and girls are equal. What does a positive difference in my means mean? If I'm taking girls minus boys, that means that if I end up with a positive answer, the girls' heights are going to be taller. And a negative answer over here means the males were taller. So this tells me in this case the males were taller. So the difference between the means, that sampling distribution has a mean of 0.67 and a standard deviation of 1.56. Okay, now, so what do you notice about the shape, the center, and the spread of the sampling distribution of your sample means of your females minus your males? So do you notice anything about the center? Ooh, notice 56.4, 55.73. How did we get that 0.67? Ooh, maybe we subtracted them. Take a look at the shape. Normal, normal, normal. Oh, they're all approximately normal. Now, the standard deviation is a little bit tricky because remember, you can't just add standard deviations. Oh, remember way back in that unit that we had a long time ago, whenever we were talking about standard deviations, you always add the variances. So let's see if we can do that to get the standard deviation right here. Okay, so both x bar 1 and x bar 2 are random variables. The statistic x bar 1 minus x bar 2 is the difference between the two random variables. We actually learned this in previous chapters. Remember that if we're looking for the mean of any sampling distribution, we actually subtract the means and it gives us the mean of the new sampling distribution. And remember, whenever we found the standard deviation, we never subtracted the standard deviation. We always added the variances. Okay, so what exactly is that going to look like in this case? So when you choose a simple random sample of size n1 from population 1 with a mean of mu1 and a standard deviation of sigma 1, and then you have a second simple random sample with a size n2 with a different mean and a different standard deviation. What is the shape going to look like? The difference of your two means is going to be approximately normal when the population is approximately normal. Now, it's not always going to tell you that it's approximately normal. However, remember, since we're talking about means here, we can use our central limit theorem, and as long as our sample sizes are larger than 30, we know that this graph right here, the difference in the means is going to be approximately normal. And remember, you can only use your central limit theorem with means. The center, or the mean of your sampling distribution, is going to be you subtracting the two means, just like we did in our previous unit. Now, this is the new part here. What's the standard deviation? Now, remember, okay, we found our standard deviation by adding the two variances. Take a look at this formula. The formula here is you're adding your two variances, but notice the difference, because remember, whenever we are talking about sampling distributions, whenever we found the standard deviation, it was always your standard deviation divided by the square root of n. Well, that's the same thing in this case. But remember, when we combine random variables, we always are going to add the variances. Well, here, we're adding the variances. Notice what happens when I square this to make it my variance. It becomes your x bar squared all over n. Oh, that's the same thing that you have right here. Now, if I am finding the difference between our standard deviations, once again, you always add the variances. This is your variance of your population 1. Then I need the variance of population 2, which I'm going to do the same thing. And then just remember that each sample is no more than 10% of the population, so you have to do your independence. The population is 10 times the sample size for both.